Lesson number 8, Daily Summary. In this lesson, we examine plots of real-life data and explore how to use the line of best fit. The table below shows the height in inches for girls of various ages. This data came from a growth chart for girls in the 50th percentile for height. So let's take a look at this table and see if we can make any conclusions. In the first column, we have age in years, 2, 3, 5, 6, 10, 12, 14, 16. So starting at 2 and going to 16, but not equally spaced numbers in between. And then we have the height of the girls of those various ages, height in inches, starting at 31, bigger, 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 all the way to 64. So clearly we can see that as a girl gets older from ages 2 to 16, it sure appears that her height is increasing. But the question is it increasing at a constant rate, or is it increasing maybe slowly in the beginning and then fast at the end, or maybe fast increases in the beginning and slow at the end, or some combination of those two things? So in order to say more than we can say just at a glance from this table, we're going to plot some points. We're going to make something called the scatter plot. So that's right down here. To display the data in the table, we use a scatter plot. We're going to let H represent the height in inches of a girl whose age is A in years. So here's our height, vertical, and then the input on the horizontal is the girl's age in years. Label the coordinates of points A and B. Let's see if we can do that now. So point A, just reading the coordinates off of the graph, I see 10 for the input and 50 for the output. So that is a girl of age 10, has a height of 50 inches. And then point B, I can see the 14 is the input, but the output is something between 60 and 65. Maybe it's 62, maybe it's 63, but we don't need to guess because these points came directly from the table. So let's look for the 14 in the table. We see, oh, okay, 14 is right there, and that means it's a 63. Okay, so that table just naturally gives rise to this scatter plot. All we're doing is plotting points. So, does the scatter plot show any relationship, pattern, or trend between the two variables? That is, does the data appear to be increasing, decreasing, or neither? Well, we saw that it was increasing before from just looking at the numbers in the table, but now we can see even more. We can see that the data gives a really rapid increase in the beginning and then kind of a slowdown and then like a little bit more rapid, and there's really not much growth between ages 6 and 10, but then there's a growth spurt, and so you get some graphical information just from this data, the scatter plot, that you didn't get just looking at the table of data. On the scatter plot, sketch a line that you think fits the data the best. So what you're going to do is grab a straight edge, and you're going to draw a line that is roughly in the middle of all of these points. And I'm going to caution you against connecting any two of the points. Do not connect two of the points. In fact, your line is probably not going to touch any of the points. But what you want to do is draw a line that captures the data the best, that is roughly in the middle of all of the points. And so you're going to draw your line, grab your straight edge. So I've drawn my line there. Should have roughly, half the points above the line and roughly half the points below. Looks like I didn't quite get there on this one. I've got, 4 points above, maybe a 5th point above, and only 3 below. So maybe my line is a little bit lower than it should be. But you're just doing your best here. And again, you're not connecting any of the points, just drawing a line that goes roughly through the middle of the table, of the scatter plot. Since the data in the scatter plot appear to be roughly linear, we can sketch a line that comes close to the data points. We say that A and H, that's age and height, are approximately linearly related or linearly associated. And I'll just say that, these data points look like a straight line would go near them, as opposed to, for example, like if we had data points that look like this, we would say, okay, that is not a straight line. Maybe there's some kind of a curvy thing that is roughly going through the middle of all those points. But in our case, a straight line does a pretty good job of being near all the points. Of all the lines that we could draw near the points, the best line, which is graphed above, has a name. We call the line graphed above the line of best fit for the data, or if you're feeling fancy, the least squares regression line, or more simply, the regression line. Important note, finding the actual line of best fit, that is the equation of that line right there, is something that calculators and computers can do, and you can too if you take a statistics course. When we draw a line of best fit, keep in mind we are just trying to draw a line that is close to all of the points. We are only going to be approximating the actual line of best fit. So the line that I drew on the previous page is not the line of best fit. This line you see here in front of you, that's the line of best fit, the one that was generated by a computer or Could have been generated by us if we knew the fancy statistics formulas to do so. We can use this line to make predictions about the data. Use the line of best fit to predict the height of an 8-year-old girl. Okay, so 8-year-old girl is right here, represented on the horizontal axis with an 8, and we're going up, and we see that we have no data point, right? There's no, the 8 is not in the data table. There's no point plotted here above the 8. But we can go to the line, and we can say, hey, maybe if the trend shown by the points in the data table continues, then maybe the data point would have been roughly on this line. And then we can come over here and read off, estimate the value of the height. And so I'm going to say that's smack dab in the middle of 45 and 50. So we'll call that 47.5. And that will be my best guess here. And that's from the graph, nothing with an equation, just reading the graph and estimating. Using the graph of the line, let's pick 2 points on the line that have nice coordinates. Note that we are picking points on the line, even though these points will likely not be any of the original data points. So what we're looking for on this line, as we trace this line, are there any points that are on this line that are also on the background grid? For example, you could pick this point right here, and you could estimate the x coordinate and you could estimate the y coordinate. But I would rather not estimate. I'd rather pick a point whose coordinates are easy to read. For example, this point right here. Okay, it's not on my diagonal line, so it's no good. But I can read the points of that coordinate because it's right on the background grid, right? It's on the intersection of the 2 of these dotted lines. So the coordinates of this point here are 14, 55. So I'm looking for a point like that, but it also has to be on the diagonal line. And so we're just kind of tracing this thing here, and we're looking for points that are on the line but also on the background grid. It's kind of slim pickings here, you know, like maybe this one is kind of close to being on the background grid. This one's not too far, this one's not too far. Sometimes it's easy to find points that are like really close to being on the background grid. Sometimes it's really not easy at all, but we're just going to do the best we can. Just so we can all be uniform, we're going to use these points here. So 335, let's find that one. So 3 is halfway here, and then 35 is right there. And so this is the point 335. It's not like on the intersection of 2 diagonal lines, but it sure looks like, I mean, it's on the horizontal line, 35, and it looks like maybe right halfway in between the 2 and the 4. So 335 seems reasonable, and it's nice integer numbers. And then the other one I said is 1155, so that's here and here. So my preference is points that are on the background grid on the as the intersection of 2 dotted lines. But in this case, we're just finding a point that's on 1 dotted line and maybe halfway between you know, 2 things on the x-axis here. Okay, so now that we've got 2 points picked, we are going to find the equation of the line that connects those 2 points, 335 and 1155. And now this is a very standard process for our class, and we can forget about all the context about height and age and everything, and we're just going to go through our normal process. Our normal process involves finding the slope of the line first. So let's find the slope. We know normally the slope is change in y over change in x, but we do not have the letters y and x. We have a and h, and you can see I've written them here. A was first and h was second. So that means that instead of delta y on the top, we have delta h because that's in the y position, the second position. Delta x is really now played by delta a. And so that means we're supposed to subtract the h's. So I will do 55 minus 35 in that order. You could do either order. And then subtract the a's on the bottom. But now you have to do the same order that we did on top. So that's 11 minus 3. That's 20 on top and an 8 on the bottom. You can reduce that fraction. Oftentimes for word problems, decimals are kind of a more natural way to represent the slope and the y-intercept that we'll find. So 8 goes into 22.5 times. So I'm just going to write 2.5. It's an exact decimal, but even if I had to round it there, I probably would write a rounded decimal. Okay, let's interpret this number. To interpret slope, I really like having my units. On the top here was a delta h. And the height was changing, sorry, the height was measured in inches. And then delta A on the bottom, that was age measured in years. And so this 2.5 is 2.5 inches over years. But I like to use, instead of the word over, I like to use the word per. inches per year. Something is changing at 2.5 inches per year. What is changing? Well, it's always the output variable, in this case, height. Height is changing at 2.5 inches per year. And so you could just say the height of the girl is changing at 2.5 inches per year, but I'll just say that the girls grow at 2.5 inches per year. Also okay to say that the height of a girl is increasing at 2.5 inches per year. Okay, let's continue to find the equation of the line, and again using the letters A and H instead of our old familiar X and Y. But we will ground ourselves in our standard X and Y equation, y equals mx plus b. But now we'll change to A and H, again just being very careful which one is which. Y was height, X was age. So there's our equation. And then we're going to replace the m with the number we just found, that was 2.5. And then I like to put a star next to that one. And then we're going to replace A and H with the coordinates of either point. We've got two of them given here. I'll focus on this first one, 335. So we'll plug in 335 into this equation here. So the H is the 35 equals 2.5 times the A is a 3 plus B. So that's 35 equals 7.5 plus B, and then subtract the 7.5 from both sides. And we get B equals, what is that, 27.5? And then we'll go back to our starred equation and write our final answer. H equals 2.5 A plus, and now we've got our 27.5. So that is the equation of the line that connects the 2 points that we picked. All right, let's rewrite the regression equation right here. H equals 2.5A plus 27.5. Now, is that exactly the equation of the line that was graphed on the previous page? Well, no, it's the equation of the line that connects these two orange points here. But the two orange points were just estimates, right? And we don't know that they were exactly on the diagonal line. We just did our best to try to find points with nice integer coordinates that look like they're on the diagonal line. So in this case, step 3, we can figure out how accurate we were when we picked nice points on the line. The equation of the actual line graphed above, according to GeoGebra, which is the software I used to make the graph on the previous page, the equation of that line is H equals 2.42A plus 28.11. And so how far off were we? Well, 2.42 was the actual slope. We came up with 2.5. That's pretty good. We're only off by 0.08 or 0.08. And the y-intercept is off by a little bit more, but not too much, right? Should have been 28.11, but we got 27.5, so off by around 0.61. Not too bad. Use your regression equation to predict the height of an 8-year-old girl. Okay, so is it H or A that is taking on the value 8? Well, 8 years old, that's the age, that's the A. Using A and H really makes this kind of problem easier than if we had done X and Y, because if you do X and Y, then you have to go back and really be careful to make sure that you plug in the 8 for the correct letter. Is 8 X or is 8 Y? No, I don't know. But 8 is the age, so 8 is A. Okay, and then you type this in the calculator or just do the arithmetic. So what is that? I think that's 20 plus 27.5, 47.5 inches. So is it close to the estimate we got in 4B? Well, remember in 4B, we looked at these blue dotted lines here and went to an 8-year-old girl and went up to the diagonal line, and then we estimated, hey, we hit it on the head. 47.5 was exactly our guess reading the graph, and the equation confirms our guess. Since we are using the regression equation to estimate or predict between known data points, the data table goes from 2-year-olds to 16-year-olds, and this 8-year-old question that we just answered is between 2 and 16. 8 is between the extremes of the data point. This process that we just followed to get the 47.5 is called interpolation. When you are in between, you are interpolating. But in part F, we're going to use the same equation to predict the height of a 45-year-old girl, and I'll just point out down below that we are about to use the regression equation to estimate or predict beyond the data points. The data points, again, are between 2-year-olds and 16-year-olds, and 45-year-old is outside of that range. And so what we're about to do by plugging 45 into our equation is called extrapolation. So if you're in between the data points, like 8 is in between 2 and 16, then you are interpolating. But if you're outside the data points, 45 is outside of 2 and 16, that's called extrapolation. So let's extrapolate with a 45-year-old girl. H is 2.5. Now A becomes 45 plus 27.5. Okay, so we're going to type this one into the calculator. So 2.5 times 45 plus 27.5, 140. Okay, how tall is 140 inches? Well, let's see, 12 inches in a foot. So that's just under 144, which would be 12 feet. So I think it's 11 feet, and it's 4 inches short. So 11 feet, 8 inches. Okay, so our regression equation predicts that a 45-year-old girl, in the 50th percentile, 45-year-old girl, will be 11 feet, 8 inches. Part G, how much confidence do you have in your answer to part F? Well, none, right? That's absurd. So the moral of the story is that extrapolation is far more prone to error than interpolation. Probably our answer for the 8-year-old girl, that 47.5 inches at the top, is reasonable. Probably not too far from the actual answer, the answer that the statistics would give us if we actually measured thousands of 8-year-old girls' heights. But at some point, our formula breaks down. Girls do not continue to grow at 2.5 inches forever. 2.5 inches is pretty close to the reality for ages 2 to 16, but at some point, girls stop growing. But our formula doesn't account for the fact that the girls stop growing. It just continues to give them 2.5 inches every year. And if you extrapolate to a 45-year-old girl, you get this absurd number. Okay, part H, use your regression equation to predict the age of a girl who's 56 inches tall. So in this case, the 56 inches is replacing which of our two variables? 56 inches is H. So 56 equals 2.5 times some unknown A plus the 27.5. So we'll subtract the 27.5 from both sides. So we get 2.5A on this side. So 0.5. 8.4, 5.42, 28.5. I think I've got that right. Yeah. And then we divide both sides by the 2.5. Okay, and I know this is silly, but I'm just going to check my subtraction real quick. 56 minus 27.5, and then we divide that by the 2.5. So 11.4. 11.4 what? Inches? No, this is an age. This is years. So if you have someone who's 56 inches tall, your estimate is that they are 11.4 years old.